Now we are going to explain about the axial flow reaction turbine. Whereas axial flow reaction turbine, the water flows parallel to the axis of the rotation, and the turbine is known as axial flow turbine. You can see that water is flow axially. Axially, water flows axially in the Kaplan propeller turbine. If the head at the inlet of the turbine is sum of pressure energy and kinetic energy, during the flow of water, a part of the pressure energy is converted to the kinetic energy. The turbine is known as reaction turbine. In the case of the reaction turbine, we already discussed. Initially, inlet we get a pressure energy and kinetic energy, whereas outlet the pressure energy is converted to kinetic energy. In case of axial flow reaction turbine, propeller turbine, second one is Kaplan turbine. There are similarly same, but whereas vanes are fixed to the hub, they are not adjustable. The turbine is known as propeller turbine. Whereas vanes are fixed to hub and they are not adjustable, the turbine is known as propeller turbine. If vanes on the hub are adjustable, the turbine is known as Kaplan turbine. The runner of the Kaplan turbine resembles with propeller of the ship. Resembles with అంటే ప్రొపెల్లర్ ఆఫ్ షిప్ లాగానే ఉంటుంది. వేరేస్ Kaplan turbine అనేది రన్నర్ ఆఫ్ ది Kaplan turbine అనేది. దట్ ఈస్ వై Kaplan turbine ఈజ్ ఆల్సో నోన్ as propeller turbine. The turbine is suitable where large quantity of area at low head is available. Low head and large quantity of water. The propeller turbines have following favorable characteristics: that relatively small dimensions combined with high rotational speed. High rotational speed means it can rotate at very high speeds, and large overloading capacity. The comparatively high efficiency at partial loads. Ability of overloading is obtained by coordinated regulation of guide vanes, whereas its guide vanes are coordinated along with the efficiencies. As per the water discharge, it will be easily coordinate, means easily worked, and runner blades to obtain optimal efficiency for all operations. And runner blades is also designed obtain the optimal efficiency. Optimal efficiency means given a good efficiency at lower effort. Kaplan turbine have adjustable runner blades that offer significant advantage to give high efficiency. In case of Kaplan have adjustable runner blades that will give high efficiency even range of partial load. Even a small loads they given a good efficiencies, and there is a little drop in efficiency due to head variation or load or variation. Head gaani load gaani variation అయినప్పుడు Kaplan turbine లో efficiencies అనేవి vary అవుతుంటాయి. Whereas Kaplan turbine is axial flow reaction turbine, we already said that the water flows through the runner of the turbine is in axial direction. Energy at the inlet of the turbine is sum of kinetic energy and pressure energy. Whereas the axial flow reaction turbine is shaft is vertical. The lower end of the shaft is larger, is known as hub or boss. It is on this hub that vanes are attached. We can see that hub, whereas the lower end of the shaft is larger. The lower end of the shaft is larger and vanes are attached on the hub. We call it as boss. Kaplan turbine is best suited where large quantity of water at low head is available. This is named after V. Kaplan, the Australian engineer. Kaplan turbines are now widely used throughout the world in high flow, low head power production, whereas low height of water, whereas high flow rate Kaplan turbines are used. The main parts of the Kaplan turbine are scroll casing, guide vane mechanism, hub with vanes, draft tube. Draft tube is one of the main component in all the turbines. Working principle: the water enters turbine through a guide vanes which are aligned such as to give flow a suitable degree of swirl. Suitable degree of swirl means whereas guide vanes are twisted so that water is in enter into the veins, it will swirl. The two flow the flow from the guide vanes pass through the curved passes, which forces the radial flow to the axial direction, which converts the radial flow to axial direction by using the twisting of guide vanes, and means aligned. Aligned means some angled, tilted. The axial flow of water, which components of swirl applies force on the blades of the rotor, loses its motion, both linear and angular motion, whereas water applies the force, linear and angular motion, momentum causes, producing torque and the rotation in the shaft. The scheme of production of hydroelectricity by Kaplan turbine is same as that of Francis turbine. Same as Francis turbine, nothing but the water is flows through the runner and hitted on the strikes on the vane blades, and it will start rotating. Is similar to Francis turbine. You can see that. See here, water is enters here and axially outwards axially. As you can see that the tilted vanes are tilted, means aligned with some angle. It will start rotating due to momentum. Comparison of the blades: Pelton wheels, Francis turbine, Kaplan turbine. In case of Pelton wheel, energy at inlet impulse. Francis turbine, Kaplan turbine, reaction turbine. Head is high for Pelton, Francis medium, low head is available for Kaplan. Flow direction tangentially, whereas Francis radially entry, axial outlet, whereas axial flow. Discharge required low, medium, high. Specific speed is low for Pelton wheel, medium for Francis turbine, high for Kaplan turbine. You can calculate it. Discharge nothing but Q is equal to area into velocity, pi by 4 d naught square minus dB square, whereas outer diameter of the runner d naught, dB is diameter of the hub, Vf1 velocity of the flow at the inlet. Some important points for Kaplan or propeller turbine are the periphery of velocity at the inlet and outlet, whereas u1 is equal to u2 pi d naught n by 60, pi d n by 60, whereas outlet diameter we are taking as peripheral velocity. The velocity at inlet and outlet is equal, and Vf1 is equal to Vf2. Area of the flow at the inlet and area of the flow at the outlet is same, whereas pi by 4 d naught minus d naught square. Next one, we explain about the draft tube, whereas you can see that the draft tube, it's increasing the area from small area to larger area. If you water goes through this small, it's changing from lower area to higher area, lower area to higher areas. You can see that 4 types of tubes: conical draft tube, simple elbow tube, Modi spreading tube, and draft tube with circular inlet, and rectangular outlet. You can see that conical divergence tube fitted at the runner exit to convert kinetic energy into pressure energy. It always increases the efficiency of the turbine. Whereas in case of turbines at the inlet, we given up sometimes pressure energy and kinetic energy. It converted into the kinetic energy and rotates the runner. After kinetic energy, it to be converted into the pressure energy. If not, the damage of tail race will be occurs. The life period of the turbine is reduces. Whereas draft tube is a pipe of gradually increasing area which connects the outlet of the runner to the tail race. It is used for discharging water from exit of the turbine to the tail race. The pipe of gradually increasing area is called draft tube, gradually increasing area, whereas it fitted at the exit of the runner. One end of the draft tube is connected to the outlet of the runner, while the other end is submerged below the level of the water in the tail race. One end outlet రన్నర్లో కనెక్ట్ చేస్తాం, వైల్ అదర్ ఎండ్ అనేది వాటర్లో సబ్మెర్జ్ చేస్తాం, ముంచుతాం. ఓకేనా? వాట్ అసలు డ్రాఫ్ట్ ట్యూబ్ ఏం చేస్తుంది? డ్రాఫ్ట్ ట్యూబ్ ఇన్ ఎడిషన్ టు సర్వ్ ద ప్రాసెస్ ఆఫ్ వాటర్ డిశ్చార్జ్, వాటర్ను పాస్ చేయడమే కాకుండా దేర్ ఆర్ 2 పర్పజెస్ ఉన్నాయి. వేరేజ్ ఇట్ పర్మిట్స్ నెగిటివ్ హెడ్ టు ఎస్టాబ్లిష్ అట్ ది అవుట్లెట్ ఆఫ్ ది రన్నర్, దేర్ బై ఇంక్రీజ్ ది నెట్ హెడ్ ఆన్ ది టర్బైన్. నెట్ హెడ్ పెంచడానికి యూజ్ అవుతుంది. అంటే కైనెటిక్ ఎనర్జీ ప్రొడ్యూస్ అవ్వడానికి ఏదైతే ఎనర్జీ అవసరమో ఆ కైనెటిక్ హెడ్ని ఎక్కువ చేస్తుంది, అంటే నెట్ హెడ్ లాసెస్ని తగ్గిస్తుంది. ద టర్బైన్ మే బీ ప్లేస్డ్ ఓవర్ ది టెయిల్ రేస్ వితౌట్ ఎనీ లాసెస్ ఆఫ్ నెట్ హెడ్, హెన్స్ ద టర్బైన్ మే బీ ఇన్స్పెక్టెడ్ ప్రాపర్లీ. మేబీ టెయిల్ రేస్ పైన కూడా టర్బైన్ ప్లేస్ చేయొచ్చు సమ్ టైమ్స్. ఇట్ కన్వర్ట్స్ లార్జ్ ప్రొపోర్షన్ ఆఫ్ కైనెటిక్ ఎనర్జీ V2² by 2z రిజెక్టెడ్ అట్ అవుట్లెట్ ఆఫ్ ది టర్బైన్. ఏదైతే టర్బైన్ నుంచి కైనెటిక్ ఎనర్జీ బయటకు వస్తుందో ఇట్ యూజెస్ యాజ్ ప్రెజర్ ఎనర్జీ. ఇట్ యూజ్ఫుల్ ఫర్ కన్వర్టెడ్ టు ప్రెజర్ ఎనర్జీ. Without draft tube, the kinetic energy rejected at the outlet of the turbine will go waste to the tail race. Tail race lo waste ga potundi and increase the net head on the turbine. We already discussed in first point. And turbine placed over the tail race. Turbine can be placed over the tail race and converts large portion of kinetic energy into the pressure energy. If they ask the purpose of the draft tube, you need to write these 5 points. If రియాక్షన్ టర్బైన్ ఈజ్ నాట్ ఫిట్టెడ్ విత్ డ్రాఫ్ట్ ట్యూబ్, ఒకవేళ డ్రాఫ్ట్ ట్యూబ్ ఫిట్ చేయకపోతే ఏమవుతుంది? సో ఇట్ ఈక్వల్ టు ది అట్మాస్ఫియర్ ప్రెజర్. అట్మాస్ఫియర్ ప్రెజర్కి ఈక్వల్గా రన్నర్ అట్మాస్ఫియర్ ప్రెజర్ కంటే అట్మాస్ఫియర్ ప్రెజర్కి ఈక్వల్గా ఉంటుంది. ద వాటర్ ఫ్రమ్ ద అవుట్లెట్ ఆఫ్ ది రన్నర్ విల్ డిశ్చార్జ్ ఫ్రీలీ ఇన్ టు ది టెయిల్ రేస్. ద నెట్ హెడ్ ఆన్ ది టర్బైన్ విల్ బి లెస్ యాజ్ దట్ ఆఫ్ ద రియాక్షన్ టర్బైన్. డ్రాఫ్ట్ ట్యూబ్ లేకపోతే ద నెట్ హెడ్ అనేది రెడ్యూస్ అయిపోతుంది. వేరేజ్ అట్మాస్ఫియర్ ప్రెజర్ కంటే తక్కువ ప్రెజర్ ఉండడం వల్ల వాటర్ అనేది రివర్స్లో రన్నర్లోకి వస్తుంది. అండ్ ఆల్సో వితౌట్ డ్రాఫ్ట్ ట్యూబ్ ద కైనెటిక్ ఎనర్జీ రిజెక్టెడ్ అట్ అవుట్లెట్ ఆఫ్ ద రన్నర్ విల్ గో వేస్ట్ టు ది టెయిల్ రేస్. కైనెటిక్ ఎనర్జీ అనేది వేస్ట్ అయిపోతుంది. Whereas turbine casing, we apply the Bernoulli's equation at point 1 and 2 and 3. Whereas I compare with 2 and 3, P2 by rho z V2² by 2z plus z plus from datum head z plus y. Whereas point 3, P3 by rho z V3² by 2z plus 0. There is no head, only there is no head datum plus hs. So P3 is nothing but atmospheric pressure. We substituted atmospheric pressure P2 by rho z V2² by 2z plus z plus y, PA by rho z plus Vy, y V3² by rho z plus Hy. Here atmospheric pressure nothing but PA by atmospheric pressure PA by rho z plus y, this value P3 by rho z value. Whereas we cancel it out, y and P2 by rho z PA by rho z plus V3² by 2z minus V2² by 2z minus z plus HF. Simplification, P2 by rho z PA minus, if you taken out, minus z plus V2² minus V3² by 2z minus HF less than atmospheric pressure. If you compare this P2 by rho z, PA by rho z minus some constant is there, it means it maintains less than atmospheric pressure. Gauge pressure, nothing but gauge pressure. To avoid cavitation, the velocity at point 3 is less than at point 2. So to compensate the pressure increase, we give the draft tube. The efficiency of the draft tube, net gained in the pressure head by velocity head, entrance of the draft tube. Whereas nothing but net head gain in the pressure head. How much head is gained in pressure head? Already given, V2² minus V3² by 2z minus HF. by V2 square by 2z. If we cancel it, angle of convergence we maintain in the draft tube is 3 degrees to 5 degrees.